Hey guys, we're Group M5. I'm Braden Coombs,
I'm Chelsea Croft.
I'm Brad Dah.
and today we're going to be talking about the advances in 3D structures in the automotive, aerospace, food, and medical industries. Okay, first off, we're going to start off with an explanation of what 3D printing is. 3D printing encompasses a broad field referring to 3D modeling technologies like fused deposition modeling, selective laser sintering, and stereolithography. Each type of additive manufacturing system has the same end goal of producing a 3D part from a CAD or digital file. 3D printing is almost a 40-year-old field, implemented first by Dr. Kodama in Japan in 1980. He implemented a system which used UV laser beams which solidified liquid photopolymer resin vapor instantly. This process was long and inefficient, and Charles Hull then produced a more efficient stereolithography system which worked similarly in 1986. Throughout the 90s and into the early 2000s, continuous innovation occurred in the field. A focus was kept on modeling simple designs with plastic materials. We then saw the inception of basic selective laser sintering and fused deposition modeling systems in 1992. In turn, new materials appeared which consisted of powders of materials and cermets, as pictured in the right figure. Today, major companies invest in 3D printing and advanced manufacturing. More high-tech additive manufacturing systems are now able to produce increasingly complex geometry parts. A focus is now put on metal material printing in the automotive and aerospace fields for high-performance parts. Also, innovative solutions in the biomedical and food industries are seen today. Applications can be seen in the accompanying figure. This is a use of 3D bioprinting. Now we look at specific advances in the automotive and aerospace field. These industries are where most advanced additive manufacturing technologies are used. New systems such as electron beam melting and selective laser melting are used to process high-performance, cheap, and lightweight parts. Systems have become automated, which require limited scaffolding and building and allow intricate design. With these new technologies comes the use of new materials, such as tool steels, stainless steels, titanium, carbon fiber, and more. From our research, we were able to come up with predictions for the future direction of 3D printing in the field. First, further materials will be developed. An increase in materials that are heat resistant, can endure intense loading, and produce more flexibility will be sought after. Secondly, an increase in metal printing will occur. As of now, plastics are currently less expensive and more readily available. With an increase in metal printing, companies will have more options when it comes to manufacturing specialty high-tech parts. Lastly, advancements in 3D printing technologies for component assembly will occur. Instead of fabricating individual parts to be assembled, it is likely advanced manufacturing technologies in the near future will be able to print and assemble parts all in one step, without the need for traditional joining processes like welding. Then we were able to predict the impacts on the industries. First, 3D printing allows companies to use minimal material to process parts. This means saving costs associated with wasted material and resources. Secondly, assembly line production will change since production teams will be given greater flexibility, since 3D printing can become a single operation with negligible setup time. Lastly, since additive manufacturing can be done at lower costs and products fabricated can be sent to clients more quick. This limits the necessity to form strategic pricing. This will allow companies to be competitive with pricing, and they will be able to price products as they see fit to ensure constant business.
3D printing can automate food preparation, improve the process efficiency, and the resultant food quality. Foods which are 3D printed enable the manufacturer to have more control over nutritional quality. A range of 3D printing methods have been utilized for complex food structures, such as selective laser sintering, hot air sintering, hot melt extrusion, binder jetting, and inkjet printing. Among them, the extrusion-based 3D food printing is the most widely adapted method. The printing technology works similar as other rapid prototyping technologies, where the CAD file is sliced into layers and prepared for physical printing. It may seem strange to print food, but some of the materials used are amplifying the possibility to create unique and complex structures. Some materials are very basic. For example, in the extrusion-based food printing, the materials are cooking materials, such as liquids like oils, soluble solids, and powder materials such as flour. In the latest research, a fish surimi gel is being tested for complex food structures. This material includes low viscosity parameters that allow for simplistic extrusion. Addition of salt to the solution increases water retention, strength, and hardness after extrusion. In the future, research can be developed to imprint large quantities of nutrients into small, printed, edible material. This application can be used to save those in developing countries who suffer from malnutrition. Other aspects that can lead to future research is creating home accessibility that can reduce on transportation costs of overseas product. This aspect can save costs for national economy purposes and reduce intake of potential wasted and rotted foods.
Now I will be talking about the biomedical applications of 3D printing. In the year 2000, a new rapid prototyping technology, referred to as 3D bioplotting, was developed to create soft tissue scaffolds. These soft tissue scaffolds act as templates for tissue regeneration and guide the growth of new tissues. The advancements of 3D bioplotting has aided in significant advancements in the tissue engineering industry, which aims to restore tissues that have been damaged by combining cells from the body with porous scaffold materials. Bioplotting technology involves a CNC milling machine, CAD, and a 3D plotter used in combination to achieve the patient-specific tissue engineering application. A liquid is dispensed from a syringe using air pressure while moving the syringe in all 3 dimensions. High-quality parts can be fabricated with user-defined porosity and interconnecting channels that allow flow of nutrient media. High-precision motors with 0.001 mm movement accuracy allow complex and reproducible inner patterns to be created. A specific example of an experiment that yielded much success in creating scaffolds for tissue engineering applications used an agar and gelatin solution. The agar and gelatin powder were dissolved in hot water, placed between 2 heated plates, and covered with silicone oil to prevent the polymer solution from drying. This solution was then casted into a mold using a bioplotter and cooled down. This process caused the solution to solidify very quickly, producing high-quality and complex hydrogel scaffolds. "3D bioplotting is currently being used in a variety of industries, with the most prominent and arguably the most promising industry being the soft tissue engineering. This RP technology has allowed medical professionals to conduct groundbreaking research and manufacturing over a wide range of areas, including skin, cartilage, bone, blood vessels, organs, and drug and nutrition delivery. 3D bioplotting has also been used to fabricate ovary implants. Scientists from Northwestern University created 3D bioplotted ovary implants and tested them on mice who had their ovaries removed. This procedure found that mice were able to ovulate, give birth, and even nurse their healthy young. Scientists also found that the prosthetic ovaries restored the natural hormone cycles of the mice. The researchers reported that the implementations of more than 2 scaffolds resulted in an 82.8% survival rate. The 3D bioplotted procedure also verified that these scaffolds are able to support the growth of blood vessels in mice without the need for additional substances to stimulate the blood flow process. Researchers from the Netherlands believe that 3D bioplotting may offer comfort to diabetes patients, taking them a step closer to being able to help patients who experience severe hypoglycemia. Their research showed that once the islet cells were retrieved from the 3D scaffolds in the lab, they were able to produce insulin and respond to glucose in the same way as a non-printed islet cell. The researchers also found that islet cells would not migrate around the body after they have been transplanted into the donor site. It is predicted that scaffolds will be able to be transplanted into patients with type 1 diabetes to help regulate their blood sugar levels. Bioplotting is also predicted to aid in the production of 3D printed organs. Carlos Carvalho, part of the Process and Material Development Department of a popular bioplotting company, says that the most promising research is being done in printing livers. The liver is the only organ in the human body that can regenerate itself, but at the same time, the only option for patients with irreversible liver failure is a transplant from a living donor. Researchers believe that in 20 years' time, we will have a fully functional 3D bioplotted liver. After discussing these 3 aspects of 3D printing, it is important to note that these applications are some of the many that are advancing today's society. Through future research and advancing technology, the world as we know it will adapt to great heights. Thank you for listening.